Okay, Year 12. So this video I'm going to talk through this chapter here. I didn't put a chapter number on it. Anyway, it's the last chapter of this 6 module. So professional. Our 6 module, which is all at the end of our acid-base reactions. And this one is called Using Quantitative Analysis. Okay, let's take a look at our inquiry question. So how are solutions of acids and bases analysed? Okay, how do we find out how much is there, basically? So there's our syllabus dot points. And what I've said underneath it for a bit of context, I'll just read out, talk around it. So there are many times when a chemist will want to determine how much of a chemical species is present. There are many methods to do this. Some we'll look at in the last module, module 8. But the earliest way to do this, I mean the easiest way to do this, is to use chemical reactions. And when you use a known amount and you react it stoichiometrically, you can determine an unknown amount. Okay, and this method is called titration. So, volumetric analysis. So from the diagram there, we've got two solutions. One we know the concentration of, one we don't know the concentration of. If we mix the two with an indicator, once they have an equal amount and reach an equivalence point, then the next part that's added in will change the indicator and we'll see our end point. So we'll get an indication of when the reactants are in a stoichiometric ratio. Okay? So, volumetric analysis involves reacting two chemical species, one of a known volume and concentration and the other of a known volume but an unknown concentration. So we'll know the number of moles of one and we'll use that to determine the number of moles of the other. So we use a visual cue such as an indicator to show this equivalence point, where they're in an exact stoichiometric ratio where neither the reactant or where neither of the reactants is in excess. Okay? Because the two species, or more, will react in a specific ratio, the stoichiometry, will determine the number of moles of the unknown species and therefore the unknown concentration. Okay, and one of the most common ways to do this is through a method called titration. So our syllabus dot point, conduct a practical investigation to analyse the concentration of an unknown acid or base by titration. We'll eventually get there, but we need to know what a titration is and how to perform it. So titration is a method that is the most common form of volumetric analysis. It involves using glassware to find the volume that a solution of unknown concentration takes to reach the equivalence point, where they're stoichiometrically equal. So with a solution of a known concentration of volume. From here, the number of known moles will equal a stoichiometrically equivalent moles of the unknown. The volume added, unknown, is also known. I'm losing words here. The volume of the unknown concentration. Once the volume you determine, you can do a calculation. That's what I'm trying to get out there. I'm finding all of these mistakes in my slides. Terrible. So the glassware that we use is kind of specialized, and it's aiming for precision and accuracy. Okay? So accuracy is getting close to the true answer, and precision is getting similar answers and also knowing things to more significant figures. So let's revisit the purpose of this glassware that you use. So the first one is this volumetric flask, this glass bottle with a thin neck and a bulbous bottom on it. I shouldn't laugh at bulbous bottom. It's a flat bottom flask with a long neck. That's a much better description past Mr. Roberts. It's a containing vessel, so we use it to contain liquids and store them. And we can only store them in one specific volume to a high precision. It doesn't have incremental volumes on there, it's just got the one. And to signify that, there's one calibration line that's along the neck at a certain height. It's usually etched in white, and we call that the calibration line. Filling it so that the bottom of the meniscus lies on the line gives a very accurate volume of 250, or in this case, 250.0 millilitres. You can also get these in different sizes. Most common ones are 25 mil, 100 mil, 250 mil, 500 mil, and 1 litre. Okay, there is little significance kind of telling you the precision. Look at this, what I've shown the bottom left there, 100 mil plus or minus 0.1 mil. Okay, so we can report that volume to 100.0 mil because we know it's really between 100.1 and 99.90. All right. So the main thing here too is with glassware, the accuracy is to do with the cross section. So notice the neck is very thin, and that's because as soon as you add one little drop, it'll go up a lot. Okay? If you think about a 250 ml beaker with a wide cross section, one little drop won't raise the level very much at all. So the thinner the cross section of glassware, the more accurate it is, because one little drop here and there will make a lot of difference to the level of the liquid. So that's why a long, thin neck with a calibration line. We've also got this other long piece of glassware, and it's also thin in cross-section too, so it's hinting at its accuracy. And it's called a burette. Now it's long, thin glass tube with a tap on the bottom, and it delivers a certain volume to something below it, okay? And it can deliver fairly precisely, and it gives increments see on here I've got 42 and 43 millilitres, so there's 10 increments in between, so it's 42.1, 42.1, 42.2, 42.3. So there's little etching at every 0.1 millilitres, okay? And it can deliver between 0 and 50 millilitres, okay? Now it starts with the 0 at the top and the 50 down the bottom. That's because of a reason. When you do a titration, you put down your starting volume and then your final volume, and then you minus the two numbers away from each other. And that way you get a positive number. If the 50 was up the top and the 0 was down the bottom, you'd minus your start volume and your end volume, and you get a negative number. So don't overthink that, and don't start to go, well, 50 minus start volume, end volume, minus them away from each other. It makes it nice and easy. Okay, the precision of a burette is greater than a measuring cylinder and less than a pipette. Think of the cross-sectional area. So these, when you see them, they're about 10 to 12 mil in diameter, circular cross-section. Okay, so that's kind of thinner than most measuring cylinders, especially a 50 mil one. They're probably about 20 mil across. Okay, how to read these burettes? We can read these burettes, and it's common practice in chemistry to measure them in millilitres to 2 decimal places. You may stop here and go, but we've only got a line that gives us to every 1 decimal place of a mil. Well, that's okay. We'll talk about that in a second, but reading it, you need to ensure that the meniscus is at eye level, okay? You don't want to read it below, and you don't want to read it above, because you'll see that there will be a slight difference, because there's a slight difference between the bottom of the meniscus and the measurement. So if you're at a lower angle, you're going to have a much lower reading, and if you're at a higher reading, a level, you're going to have a much higher reading. So you want to be at eye level, and that's called parallax error. Okay? If you're having trouble seeing through there, if there's stuff behind the burette where you can't read it too well, what you can do is put a white card behind there, or a different colour, so that it's a bit easier to read. And you can also sometimes get burettes where they have printed white behind there, and they sometimes make it easier to see too. So back to reading this to two decimal places, I should say. Okay. Now what you can do is have a look and read it to the first decimal place. That's nice and easy. What line is it close to? Okay. And then what we tend to do as chemists is the second decimal place, we either designate that as a 0 or a 5. Now if the bottom of the meniscus is right on the line, we write down the second decimal place as a 0. But if it's just above, what we do is we write it just, if it's just above, we put a 5 there. Okay, so for here, let's say that we're reading it in the image there, we've got 9 point, it's kind of hard to see, there's the 10, and it's kind of close to the 2 one back. So that one that's just underneath the meniscus there is 9.8, but it's not really on that meniscus. So it's not actually on 9.80. So I would read that as 9.75 because it's below the 7, but above the 8, 9.75 milliliters. And I pulled this image off the internet. That's not my favorite, I can't even think of the word, nail polish color. It's quite pretty though. Okay, how do we fill, or we need to talk about pipettes. So pipettes are vessels that we transfer liquids in. Okay, it's a delivering vessel, and for the most part, it's very long and thin. Okay, we use these ones that I'm showing here are called bulb pipettes because they have that big lump in the middle, and we call that the bulb of the bulb pipette. So they can measure with high accuracy and precision because where they have that volume line, the calibration line, very thin cross-section. It's only about 3 or 4 millimeters wide, so it's quite accurate and precise. Excuse me. So we use these. The only trouble is they can only measure one volume, where the calibration line is. They can't measure anything else. And to fill these, well, back in Mrs. Dennison's day, what they do is just put their mouth on the end and suck that up. But the trouble is that you don't know where the pipette's been before, but you don't want to be really sucking up stuff like dichromate, all these toxic things. So we've got these things called pipette fillers, and there's 2 there in the red with the black background. There's that bulb one and that, I forget what it's called, but we use them in the lab, and they're called bulb fillers or pipette fillers, and they suck the liquid up. Okay, and what we need to do is, I've shown you in another video, is you suck the liquid up above the line and then take the filler off, put your finger on, and then use your finger to lower the level. That gives you a much precise reading and level, because the best trick to do when you have a pipette filler on there and you think you've got it to the line, just shake it up and down a little and you'll see that level goes up and down dramatically. Okay, so these tend to come in set volumes. I've got pictures of them there. So there's 100, there's a 50, 25, 10, and there looks like a 5. You can sometimes find 15s as well, but we'll most often use the 25 mil. And there's someone down below that I found a picture of someone using a pipette. Now, she's not wearing any safety glasses. Pipettes are really hard to fill, especially, do you see how she's using her thumb for the seal there? She's wearing gloves. That's very hard to do, and you don't get a good seal, and it's hard to get the liquid level at the calibration line. So often you'll see chemists, it depends on what they're using too, but if you're using a pipette and lowering the level, it's easier to take your gloves off if you can. But she might be dealing with something very toxic there. But if she is, why is she not wearing glasses? Anyway, I did like that photo. There was probably terrible, terrible stock photos there. That was probably one of the best. Okay, so I take you through how to use a pipette, and I've just talked through a bit of that. I've got a video link there, but I might show you how to do that by video anyway. Okay, the main thing is when you're rinsing it, you've got to rinse with what you're delivering in there. That way you can deliver the known number of moles and you're not diluting it. Okay, reading with accuracy. So this parallax error. Okay, so if you're looking down from above, you're going to get a lower reading, and if you're looking up, you get a higher reading. But if you're looking straight across, it's going to be as correct as you can get it, as accurate as you can get it. So hold things up to eye level. Never lean down. Never lean on the floor of a lab because you've got broken glassware and who knows what on the floor. And also you're putting your face at spill level. Lift things up to your eyes. And look at this person in the photo. They're wearing safety specs. Good job. Okay. That's what I was just talking about. So, how to use a bulb pipette. I was looking for videos and obviously I saw this lady leaning down on the bench. What's she doing? She's at spill level. That's terrible. Who knows what's on the floor as well, so don't do that. And then I had a paranoid feeling that she might have been a little person. And I checked the rest of the video and saw her stand up. So don't do what poor Nikki here is doing. Don't lean down at spill level and kneel on the floor. Look at these two lovely people down below here. Pipetting technique and fill the pipette with sodium carbonate, holding it up to eye level. Brilliant work there. Don't go picking on Nikki though. Okay, how do we identify the endpoint? So for most of these acid-base titrations, we're going to use an indicator to show the endpoint. And we need to learn the skills of choosing an indicator. Okay, and an indicator is going to show us a color change at a certain point. Say if you're adding a base to an acid, okay, you're going to reach the equivalence point, and then the drop of base beyond the equivalence point is then going to react with the indicator and change its color. Okay, and that's what's happening in the top GIF there. Adding the base, and it's reacting with the hydrochloric acid. And as soon as all the hydrochloric acid is gone, the base reacts with the indicator and it turns pink. Okay, so that's the phenolphthalein endpoint they're using there, and there's a diagram below. So on the left we've got our acid in there, and in the middle, as we're adding it, we can see kind of the pink forming where there's a lot of base, but usually while you're swirling it, it disappears and goes clear. But once we go beyond the endpoint, it goes to the pink, where the excess base reacts with the indicator and it turns the phenolphthalein pink. Below there, we've got a different indicator, a blue to white one. I'm not too sure what that one is, but it looked kind of cool, so I'll put it there. So when your indicator turns color, we call that the endpoint. And the idea is you want that endpoint to be as close as the equivalent point as possible. Okay, we'll talk about the difference more, and you'll see it in graphs where they're not as accurate as they can be, where they don't meet up. Okay, so we need to learn the skills of choosing an indicator, and I recommend that you remember 3 of them. Here they are in the chart: methyl orange, bromothymol blue, and phenolphthalein. Okay, they cover all the bases between strong, weak, and strong, and let's not worry about weak actually, and we'll talk about why. So methyl orange in the acidity range is kind of a red colour, and then between 3 and 4 it's orange, and above 4 it's yellow. So it's a really good indicator if you've got an acidic endpoint, okay? And you'll have an acidic endpoint when you have a strong acid with a weak base, okay? That's your ideal indicator there. Bromothymol blue is yellow in the acid range, and between 6 and 7 it changes from a green to a green, and then above that to a blue. Okay, so it's a really good indicator when you've got a neutral salt endpoint for your neutralization, when you've got a strong acid with a strong base. And then we've got phenolphthalein that's clear below 8, and between 8 and 9 it's a light pink, and then after that it goes to a dark pink. Phenolphthalein that change at around 8 to 9 is a really good basic endpoint when you have a strong base with a weak acid. So if you remember all those 3, you'll get by. Someone's waving to me from another room. Rude. That's Mr. Spratt and Miss Bub. Okay, so if you remember those 3 indicators, you'll be good for any situation in the HSC. Remember those three indicators, what colours they are in that range and what colour they change, what pH they change at. Okay, you got enough to do 7.1. Let's keep going. So we need somewhere to start. We need a known concentration. And that can be hard in some ways. And one way we choose to get around that is to use something that we call a primary standard. So a standard is just a solution that we know to accurate concentration. Okay? A primary standard is something extra. We need something that is reliable. So to accurately determine the concentration of an unknown solution, a solution that will react and with an accurately and precisely known concentration is needed. So a solution made from a chemical substance that will achieve this is called a primary standard. So primary standards are special. They're a really good starting point. We can know the concentrations of these solutions very accurately because we make them from a salt, so from a solid, and we dissolve them. And it's a solid that's very unreactive to the air and to other things that could interfere with it. We only want it to react with what we eventually want it to react with. We don't want it to be doing all these side reactions and losing concentration. Okay? Some of the most common substances that are primary standards are anhydrous sodium carbonate, so sodium carbonate without any waters attached, and also sodium hydrogen carbonate or sodium bicarbonate. Okay, so the diagram down below, we get a salt, we dissolve that in a volumetric flask, and we make it up to the line. Okay, so the criteria for a primary standard are that they must have these properties. They must be made from a solid that will dissolve in water. They must be soluble. Now, there are some weird instances where you'll be doing chemistry and they won't involve water, but in this course we'll always be involving water. So for us, a primary standard will always dissolve in water and have a high solubility too. Okay, it must be able to store over a long time under laboratory conditions. So it can't react with air or even water because of humidity from the air. Okay, it must be able to be acquired in high purity. Yeah, you must be able to get a high purity sample, because if your sample's only 95% what you think it is, what's the other 5%? Is it going to interfere with your reaction? So you need very high purity in your solid that you're going to use for your primary standard. And it can't have any waters of hydration. It must be anhydrous, so it can't form water of crystallization. That adds an extra layer of uncertainty in there. Okay, they're the must. There's three more here that are ideal. Okay, sometimes you might not be able to get it under very special circumstances. We might kind of sacrifice one of these ideals, but usually we'll try to get there. Okay, so ideally it will have a large molar mass. And what that will do is it will give us, when we weigh it out, more significant figures in our mass. And therefore more significant figures that we can carry through for our concentration. Okay, if it's a very low molar mass and we add a very small amount, we might only be able to make up a primary standard with one significant figure in there, and that's useless. It's not going to tell us much at all. We're aiming for high precision, we're aiming for a lot of significant figures. So a larger molar mass will give us more significant figures going in and more significant figures for our concentration. Okay, ideally it has to be non-toxic. The less toxic substances that you're working with, the better. The less cleaning up you have to do, the less disposal. Okay, I think I've said enough about that one. Being cheap and affordable to use. Ideally, if you find something that will only react with something expensive, you want to find cheaper options, yeah? You don't want to waste your money. Okay, so they're the musts and ideals for primary standards, okay? I'll talk a little bit more. Let me talk about some examples. So often we use standards or solutions in our titration. One of the most common ones we use is sodium hydroxide because it's the ideal strong base. It's very common to use. The trouble is it doesn't store well as a solid, and that's because it reacts with water very well and absorbs water from the atmosphere. And the term for that is hygroscopic, with a G, hygroscopic. It absorbs water from the atmosphere. So if I wanted to make up a primary standard of that, I'd calculate what mass of sodium hydroxide I need to get the concentration that I want. And I'd weigh out that solid salt, and I'd weigh it out and I'd calculate the number of moles in that solid, and I'd put it in. The trouble is that I'd actually have a lower concentration because some of that mass that I weighed out is actually water in there too. So it's not a very good primary standard because it reacts with water in the air. So whatever I weigh out, I'm actually getting less sodium hydroxide because I'm weighing out some water. So sodium hydroxide is not a really good primary standard, but it is a decent secondary standard. Okay, and the secondary standard is a solution that's been titrated against a primary standard so that we know its concentration accurately, the true answer, and also precisely to a lot of significant figures. Okay, a secondary standard does not need to fit the criteria of a primary standard. Okay, it doesn't need to be as stable and long-lasting. Okay, we can make up a sodium hydroxide solution and use it for a couple of days or a bit longer or a week or so and kind of know that it hasn't degraded. But once it gets older than that, well, it's hard, it's doing some side reactions and doing some different stuff. There'd be less sodium hydroxide in there than what I'd predict. Okay, so it can't be stored in the long term. So secondary standards are just kind of short-term ones. We've titrated it against a primary standard. We know its concentration accurately in the short term. Okay, there's another term that we use which is a working standard. That's just whatever standard we're using with the reaction. Okay, it could be a secondary standard, or it could even be a further one, a tertiary standard that's being used. Okay, it's also a solution that we know its concentration accurately and precisely because it can be tracked back through a series of titrations to that primary standard. Okay, again, it's used in the short term and may degrade over time. Okay, I've just thought of a problem here. Say you have a sample of hydrochloric acid that you don't know the concentration of, and you want to the only base that you have is solid sodium hydroxide. Now the trouble is that solid sodium hydroxide is not going to make a good primary standard, okay, because it's hygroscopic. So it has to be a secondary standard, okay. So what you could use for a primary standard instead is you could use some solid citric acid or maybe some KHP like we did. That's very stable and meets the criteria for primary standard. So we can start from an acid primary standard, and because our unknown's an acid, you can't react with an acid, so you've got to do a secondary standard. So then our solid sodium hydroxide could be our secondary standard. So we could titrate the sodium hydroxide solution that we made up with our primary standard, say we've made it out of KHP, get the concentration of the sodium hydroxide known accurately and precisely, and then finally react that with the hydrochloric acid to determine its concentration. So sometimes our titrations can go in a series of steps where we might need to think about the path that we'll get to finding out our unknown through a series of titrations and a series of different standards. Okay, there's two good videos about making up standard solutions and making up primary standards. Okay, and we'll do a prac of that too. Oh, we did a prac with the KHP. Check your understanding 7.2, you've got enough skills now. So how to prepare a titration. Now we're gearing up to make a titration. And first thing that you need to do, we need to talk through cleaning all this glassware. There's a specific way we need to clean these. So with a burette, okay, we clean it with the deionized water first from a wash bottle. We do at least 2 of those. What we need to do is close the stop bottle, put about 10 ml of water in, maybe a bit less, rinse through the stop cock, and then also put your finger on the end, as long as it's safe, and then tip it upside down and make sure you rinse all the way to the top, and then get rid of that water. Okay, If there's a lot of water sticking to the side, that says you might have contaminants on the side. You might want to get a bit of soap and water in there too. But you won't get rid of all the water on the side, okay? Now, if you put your known concentration in, or something that you're determining the concentration on, and it's got a lot of water in the side, you're diluting it. What you're doing is you're already diluting it. You won't find the concentration of what you originally had. You'll find the concentration of your now diluted sample. So what we do to get around that is we rinse the burette with the solution that is going to be put in there. Okay? And so a small amount of what you're putting in there, rinse it through twice, get rid of that, whatever's left over, and then fill the burette up to the top. Okay? After that, underneath the burette, we're going to have a flask with something that's going to receive, okay? And we're going to, whatever's in that, it's usually a conical flask, we need to pipette a certain amount of volume in, okay? And we need to clean that pipette out first 2 times with water, and then we also clean the pipette with whatever we're going to deliver in it. Say if we had some water left in the side and you fill it up to the calibration line, you've just diluted your solution. So what you do is rinse the pipette also with the solution that you're going to deliver. So rinse it a couple of times with a little bit of the solution, make sure it goes all the way to the top, put that in the waste, and then once you've done that twice, fill it to the line. Okay, and then we're going to add indicator to our flask below. Okay, and it's going to look something like this. So we've got our burette clamp with our burette, and that's hovering. It's clamped over a conical flask with something down the bottom and our indicator in. Now, have a look here. They've got the titrant up the top, whatever's in the burette, and it says what that's going to be, whatever it is at known concentration. And down below, it's going to be what we're looking for, our unknown concentration. This is not always the way. There's some rules around this that people say, but they're quite interchangeable. By the end of the titration, you're going to know both volumes used, and you're going to know the concentration of one. It doesn't matter whether it's down the top, down the bottom. But what I'll come to is you need to design it so you're going to get the best indicator transition or the best endpoint to see. Okay, so here is another diagram. And what they've got is they've got an acid base one here. And it must be a weak acid with a strong base because they're using sodium hydroxide and they just mentioned acid solution. And they've used phenolphthalein because it's clear going to pink. So it must be a weak acid that they're using here. So they've done this right for this way because for phenolphthalein, it's easiest to see once it just has a tinge of pink. That's a really good endpoint. If you're doing it the reverse and you put the base down the bottom and the acid up top, you're going from pink to clear. It's really hard to finally tell when you've lost all the tinge of pink that you can to find the endpoint. It's much easier to see the first tinge of pink appearing than the last tinge of pink disappearing. So that's how you design a titration. You design it with the best endpoint to see, and then you put whatever needs to go into the burette and whatever needs to go into the bottom. Doesn't matter which one's unknown. Okay, now you've got enough to do the Ed Rollo titrations videos. And I've given you a couple more there that I found on YouTube. Okay, and we can do this practical. I haven't filmed this one yet, but we'll slot it in. Determining the concentration of ethanoic acid in vinegar. So with our titrations, we have to do calculations afterwards once you've identified that endpoint. So they can tend to be long, but they base themselves around the same idea, okay? You need to calculate how many moles of your known solution you have. And you'll know that because you know the concentration and you know the volume that you use to reach the endpoint. After that, once you know how many moles of your known, you connect it to how many moles there must have been of your unknown at the equivalence point by the stoichiometry. Once you know how many moles there must have been at the endpoint of your unknown, you can look at the volume used. Moles divided by volume will give you the concentration of your unknown. So the main idea here is this process is like well, it is a process. Once you've done lots of example questions, it's very hard to forget. So do lots of practice calculations for your titrations. Okay, when we do a titration, we always do repeats. We don't usually do one, okay? And that measures the reliability in what we're seeing here, our numbers. So it's easy for a beginner to make errors in titrations. So that's why we repeat it, repetitions, okay? Now, different sources where you look online will have different rules on how many repetitions you do, how many titrations you do. But the thing that most chemists say is there's not a fixed number. What we try to do is have different standards for how agreeable our total volumes are. And for university, undergraduate university, and what I recommend for year 12 is we would like 3 titrations that are within 0.20 millilitres of each other, okay, and we call them concordant ones, okay. Once we have 3 of them that are within 0.20 millilitres of each other, we know we've done a good job, okay. So looking at the top diagram here, we've got 23.65, 23.95 and 23.7. So the top and bottom ones are well, they're all within 0.30 mil of each other. So we haven't got 3 concordant ones. If we do a 4th one and we get the 23.85 like in the diagram, the table below, we've got 3 that are concordant, okay? And so then when we do our average, we don't discard the one that's the slight outlier. We still take that in consideration when we're doing our average volumes. So we still add those 4 numbers together and divide it by 4. But that's the method that we do. One of the main questions that I get from when people are doing titrations is, oh, should I do another one? Or here's your rule, have you got 3 within 0.2 mil of each other? So as I was saying earlier, it doesn't matter where you put the acid or the base, or your known and unknown. You're designing for the best endpoint, okay? So you're deciding on what in the flask down below will be the easiest one to see. And in the diagram here for phenolphthalein, it's easier to see the clear, the left going to the right and seeing the appearance of light pink than it is the other way, going from right to left, going from a pink until you can't see any more pink and it's clear. So when you're using a phenolphthalein endpoint, you put the acid down the bottom and you put the base in the burette, okay? It doesn't matter which one's known and unknown. So here I've done you up a table of the 3 indicators. So phenolphthalein, it changes to around 8. You want to put your base in the burette and your acid down below, so you get the white or the clear to pink transition there. Look at that little animation, isn't that great? Okay, so for bromothiamyl blue, the best endpoint is from the yellow to green. Okay, so you want to, again, put the acid down the bottom and the base up the top. So you get the green in between. Okay, and for methyl orange, the easiest to see is from the yellow going to the orange, and that's your endpoint. So again, you're starting with the acid down the bottom and your base up the top. Okay, so for our 3 indicators, it's worked out nice and good that you can remember if you put your acid down the bottom and your base in the burette, you're always going to be right for the HSC. But if you're using a different indicator, you're going to have to work that out and design it for yourself. But coincidentally, those 3 worked out really well. So if you put your acid down the bottom and the base up the top, no matter what indicator you're using, you'll get the best endpoint to see. All right. What's the next concept? Oh, our models. What I might do is stop it there and do a separate video on these models of neutralization. Oh, actually, no, I'll keep going. How professional. I'll just do this one. Okay, we need to model a neutralization of strong and weak acids using a variety of media. So we're using Keynote here because I thought that'll be good for while you guys are in quarantine. So what you needed to do is copy-paste these symbols of our solution during the titration. So here at the beginning, on our left-hand side, we've got a beaker here, and we've just got some water and we've added in a strong acid. And how do I know that? Well, because there's none of the original acid left over, the HCl there. It's all completely ionized. We've got chlorides left over, and we've got hydroniums. Okay, it's a very strong acid because it's gone to completion. It's reacted fully with water, and there's none of the HCl left over. There's chlorides and there's hydroniums. Okay, and there's 5 moles of there's 5 moles of hydrochloric acid that have gone in because we've got 5 chlorides and 5 hydroniums. Stoichiometrically, we're all good. Okay, so at the beginning we just have those that I've just talked through. We've also got 3 molecules of water there. Okay, at the start of the reaction we're going to add, so think about the burette up above that has some base in there, 3 molecules of sodium hydroxide. Add them in. Okay, and what they do is, because they're in solution and they're a strong base, they ionize and they react. Okay, so our 3 molecules went in of sodium hydroxide. The sodium pluses are very weak acids, so they just associate with themselves. They don't react with water. But the hydroxides react with the strongest acid in the formula, which is your hydroniums. So we've just taken out 3 hydroniums. We've just started neutralizing this reaction. So we've lost 3 hydroniums, we're down to 2 hydroniums now. So it's less acidic. We've only got 2 hydroniums. So we're on our way to our equivalence point. We've added 3 moles. Okay, now we needed to show our mixture at the equivalence point. I didn't do an animation for this, but what you can see is I've added 2 more molecules of sodium hydroxide in there, and I've got no hydroniums left. There's neither hydroniums in excess, and there's no hydroxides there either. We're at the equivalence point. We've got none of the reactants there. We've got no hydroniums and no hydroxides. We've just got waters, and we've just got sodium pluses and chloride minus. We've just got salt and water. This is at our equivalence point, okay? So we've got 5 sodiums and 5 chlorides because we had to add 5 sodium hydroxides in to neutralize our 5 hydrochloric acids. Okay. Beyond the equivalence point, let's add in 3 more sodium hydroxides. They just dissociate, form sodium pluses and hydroxide minuses. Notice that there's 3 hydroxide minuses now. We've got the base in excess now. We've gone past the equivalence point. It's now basic. Okay, now you can do this ed rollo. And I think I'll call it quits there and come back for a part 2.